Hello everyone, welcome to Unit 7. My name is Shuang Ma. I'm currently a postdoc working at NASA Jet Propulsion Lab at Caltech. My research interest is in global estimates of wetland methane emission. In the previous lectures, we learned the theory of data assimilation. We got an idea of how it works and how it helps constraining the parameter values. We practiced running data simulation using simple structure models, for example, the matrix form of TICO. Well, in the next 3 days, we will get into something even more exciting. We will practice on running the complex terrestrial ecosystem model, do data assimilation, and then ecological forecasting. In this lecture, I'm going to introduce applications of using data assimilation framework at the spruce and peatland responses under changing environments experimental sites. The model we will be using is the conventional form of TICO. One thing I want to clarify here in the beginning is that you might get a little confused by different versions of TICO, especially the matrix version you've been working on in the previous lectures. Conventional TICO is the more complex version of TICO that's organized by conventional equations and have meteorological variables as input. However, the TICO matrix uses NPP as an input, which means the conventional TICO 2.3 have its own photosynthesis module built in. Also, at the same time, it covers all the key processes within the land system model, which include surface energy fluxes, hydrology, and biogeochemical cycles. The advances of working on data assimilation with conventional complex models is that modelers can assimilate any detailed observation data into the model. For example, soil carbon content, foliage biomass, soil respiration, as well as some very specialized data sets such as isotope soil carbon content, dissolved inorganic and organic carbon content, and also plant-mediated transport of methane from different plant functional types. Water table level, it really varies upon your scientific question and research interest. Based on how these observations improve models' performance, we could directly offer advice on fieldwork strategies such as sampling time intervals and also which data set to keep measuring in the next year given a limited resource. So this framework is a great tool for studies at experimental sites, especially with intensive field measurements. There's obvious drawback of using the conventional model in data model fusion because more details in the model equals to a larger computational cost. In this, with TICO 2.3 data simulation mode, running a full iteration of data model fusion to get a stable chain will require about 8 hours on a single site. I was lucky to work with a scientific team at a northern Minnesota peatland where significant amount of soil organic carbon is stored 2 to 3 meters deep due to the year-round inundated condition and the low temperature. Because this type of ecosystem stores 1/3 of soil organic carbon on Earth, how this carbon will respond to warming is a big concern. The scientific questions within this project include, will whole system warming in the future release accumulated carbon from peatland, and how fast this will happen, and also in which form of carbon will it be released. To answer these questions, scientists have heated up this whole ecosystem from above to below ground at 6 warming gradients from 0 up to 9 degrees Celsius, and made a bunch of measurement of carbon fluxes and storage at different levels. My first study in this project is to use model to predict methane emission under warming. Methane had 45 times warming potential of carbon dioxide over a 100-year scale. It is directly responsible for approximately 20% of global warming since pre-industrial time. However, wetland source methane emission have been a principal source of uncertainty in the global atmospheric methane budget. The figure on the right shows global wetland methane emission budget estimated by different methods. The second column is showing the estimate from different process-based model, and it is showing the largest disagreement between different model members comparing with other methods. You may wonder why we're still trying to use process-based model to make predictions. One obvious reason is that process-based models have the predictability to give estimation of methane emission in the future scenarios. And secondly, it also provides prior information, which is very important for the top-down research methods. There are three major sources of uncertainty in model estimated net methane emission. First is a under-described model structure. That is because of lack of empirical data to help build up a mathematical equation to describe that specific process. For example, the pH and the redox potential effect on methane oxidation is under-described in the model, and the problem is that we don't have much data to validate the model results. And the second point is because of the uncertain prior range of parameter values. Each parameter spans a certain range of possible values from empirical studies, and sometimes manually tuning the parameter values to match the observed methane fluxes could be self-intuitive and could be getting the right answer with the wrong reason, and that is very dangerous, especially when you use the tuned parameter values to project for the future warming scenarios, etc. The third uncertainty comes from a poorly mapped wetland area, especially if we consider the seasonal inundation that dramatically change the area of wetland. And another example is satellite observations cannot capture the wetland area with intense vegetation cover, and these regions are often ignored in these satellite-derived maps. In the 1980s, we started putting together mechanistic equation to describe the methane emission process. And decades of modeling research on methane have evolved to a stage that the emission pathways are explicitly calculated with various complexities. However, few studies have evaluated the information from observation data to reduce uncertainties in parameter values. So the first scientific question in this study was to figure out what information can we derive from observational methane data to reduce the uncertainty for process-based model estimations. And secondly, we want to know how will methane production, oxidation, and transport pathways will respond to warming. To answer the first scientific question, I intended to use data model fusion to see which parameters could be constrained by observation data and what are the corresponding processes linked by those parameters. The data I had was from 2011 to 2016, which is the net methane emission from using the static chamber method. There were in total 30 data points that were from 2011 to 2014 for data model fusion, and the rest of the data points from 2015 to 16 were used for model validation. I used the model TICO and developed the methane module based on the original TICO version. I fully represented the state-of-art knowledge in methane emission, which include 3 major transport pathways, which include plant-mediated transport, diffusion, and ebullition. And methane production and oxidation and all the processes are realized in 10 different layers vertically. And the methane module is coupled into the respiration module and also affected by soil moisture, porosity, soil temperature, and atmospheric pressure. The data model fusion algorithm I used is the adaptive metropolis Hastings algorithm. Here it shows the logic flow of data simulation written into the source code of the TICO data simulation framework. At each iteration in the chain, a new set of parameter values is randomly chosen. The model generates result with these parameter values, and then the disagreement to the observations is quantified using the cost function. The cost function aggregates a total model data mismatch value, J new, for all the 30 time points. In this example, since we have 30 near monthly net methane emission observation. In this study, n equals 1 as we only have one set of parameter data, which is the emission rate. We save modeled methane emission as xt. When the corresponding observed methane emission is available, which is zt at time t, the standard deviation is considered as the confidence level of the observation. In this study, it reflects errors from instruments, measurement, and spatial temporal heterogeneity. This is used in the cost function to adjust the weight of model data mismatch for individual data points. Now let's dig into some results. The posterior distributions reveal that both of the methane production-related parameters are well constrained by just using the methane emission data. To quantify model uncertainty due to parameter values, we can then randomly draw sets of parameters from the posterior distribution and then run the model with each of them, resulting in a distribution of outputs for methane fluxes. In this case, we perform 500 simulations with different randomly drawn parameter sets. The forcing data beyond 2016 was statistically generated based on the historical meteorological data over the past 50 years. It is apparent that the data-constrained methane simulations match both the magnitude and seasonal variations of observation reasonably well for both the 2011 to 2014 calibration period and the 2015 to 2016 validation period. The model tracks the interannual variability of the measurements, notably including the spike emission in 2016. By comparing the seasonal variation of methane emission to environmental drivers, we find that methane emission is dominated by surface inundation and soil temperature. Soil temperature is the restricting factor below 10 degrees Celsius, but the water table level controls peak growing season methane emission when soil moisture is well in the active range for methane processes.
Methane emission is more sensitive to soil temperature during the wet period when the whole soil column is inundated. The data-constrained parameter probability distributions were then used to predict methane emission response to warming. An increase of 2.25, 4.5, 6.75, and 9 degrees Celsius in both air and soil temperature is added into the model to drive the methane emission. This is a set of warming scenarios corresponding to the experimental warming treatment at the spruce site. We find exponential increase of methane emissions in response to warming, shown in the figure A, with 4 times increase under plus 9 degrees Celsius warming. We also find that the uncertainty in plant-mediated transport and abulation increases most under warming, and they contribute to the overall change in methane emission uncertainty, which is shown in the panels D to F. In summary, this lecture shows how data assimilation is applied to reduce the uncertainty of modeled methane emission in a northern wetland ecosystem. The data assimilation approach used in this case study enabled parameter estimation and uncertainty quantification for forecasting methane fluxes in response to climate change. More observational data streams, such as methane production, plant-mediated transport, abulation, and diffusion, may be able to constrain more parameters to further improve model accuracy and reducing the uncertainty. This is part of my PhD work, and I appreciate the help from project collaborators. Thank you all for watching the video, and hope to see you again in the practice session.